So today I want to kind of more focus on some of the issues which we face running Docker in production. And we've got fairly unique circumstances which are actually fairly generic at the same time. So my name is Ben Hall. I'm the founder of Ocelot Uproar, and we're a software development studio here in London. We basically build prototypes for companies, train them on using technologies such as Docker, and we also build our own products. One of which is Brownbag, which we like to think as Netflix for developers, and the other is Catacoda, which I'm going to go into more detail later. And basically what I want to talk about, and the premise of this talk, is what happens when you give a user, which is completely anonymous, complete access to a Docker container and a Docker server, and how did Docker actually secure the interactions and secure what the user's doing and your infrastructure as a whole. So Catacoda is an online learning platform for developers. And so we have environments such as Ruby, Java, and exotic things like Elixir accessible that you can use in the browser with a very simple IDE, which is all synced, and you can run code. But we also have things like Docker running. So you get a private sandbox Docker daemon, which you can start learning, you can start playing, you can start understanding more of the ecosystem, all within your browser, all within a second or two. And you have it, and if you want to delete it and start again, then you just hit refresh, and it's all back fresh. And this introduces some security issues, because we're giving people complete access to a server. And this is very similar to the problems which you have if you're running multi-tenanted, if you're running a PaaS and code which you don't particularly know where it came from, or it's not particularly trusted. But even things like continuous integration servers, where the code hasn't been tested yet, and so you don't know what side effects it has. And so these are problems which we're facing, and generally it's just more about Docker security best practices, which we've had to implement and had to learn. And a lot of the things which users do initially are things which instantly get you put on the naughty list, and are things which they purposely try and break the system when they first get to it. And every single user who comes onto the platform, they instantly go, oh look, a terminal. Well, let's see what we can do. And so they run through this kind of series of patterns, and it's always the same pattern. So who am I? Oh, look, I'm root. Excellent. Which directory am I in? Ah, well, I'll just break out that. And then they start installing some stuff, think they're clever, change some passwords, and eventually they get bored and they just delete everything. And that's fine, because it's Docker, and it's running in a container, and so they can do this, and you can get away with it. And it's surprising how many times this has actually happened, because my test scripts have kind of accidentally cleaned up one or two directories too high and deleted a build agent by accident. And so that's a little bit embarrassing. So just running things inside a container just stop you doing that anyway. So that's nice. And obviously they're root, so they think they're powerful and can do everything which they want. But we just add a new user, run it as a user, and they see they're not root and they kind of get bored and go away. Some users try to investigate a little bit more, so they start poking around, seeing the uptime, seeing how much free space, free memory and stuff. And this is just kind of frustrating. Because Docker is only providing kernel virtualization, all of the kernel information like uptime and memory gets leaked back through and leaked to the container. And so this is the difference between virtualization for like a hypervisor like ESX or VMware or Hyper-V, because they're isolating and they're virtualizing the kernel too. And so this is one of the Docker-y aspects, and you kind of just have to suck it up. They can't do much with that information, so they can see how much uptime it's got. It's generally either 1 day or 1 week, then everything starts to break, so I have to reboot. But generally it's that information. Not very interesting, not very important. Then they go, ha, right, that's not very interesting. They agree with me, so they try and reboot or they try and shut down the environment. Obviously, it's a container, so they're not really going to get very far. That is, unless you run with net equals host. And because this changes the namespace which the container is running in, and it changes the namespace from being isolated to being the network namespace, then things like reboot and things like shutdown do actually cause the whole system to shut down, because you're elevating the container beyond what it's supposed to be doing. And this has advantages, and there's reasons why you want to do this, but there's also reasons why this is bad from a security point of view. In 1.9 and 1.10, they're going to change this, so it's harder to do and harder to break out your namespaces, which is probably the better thing for the environment. But generally, like I said, most of the things which Docker provides for security is secure, right? Out the box, it's a container, it's got nice namespaces, it's not good C groups, it works, but not everything. So CPU shares are very good. For example, if someone wants to write an infinite loop and they want to use up all the CPU usage, having CPU shares allows you to mitigate and allows them not to take over everything running on a system. And so you can say this container can only have maximum 50% usage and it has to be shared with all the other things on a system. And so that gets around a lot of the issues which we're facing until you get to this lovely bit of code. And this is what's generally referred to as a fork bomb. As we do, we define a new function called colon and open parentheses, which calls colon, which pipes you out to colon, which is itself, which then releases control, and at the end, when it's done defining itself, calls itself. And so very quickly and very instantly, you've got one function calling 2, calling 4, and it gets massive. And you can see this happening because your system load kind of goes to 4,000%, and there's like 7,000 processes running on your system before everything calls to a halt and dies. This is a problem. In Linux, we've got ulimits, and so we can limit the number of processes which are running on a host. And so we can limit, for example, don't run 7,000 processes, like keep it a normal number. The problem with Docker is, at least in the current version, this is on a per user basis. So if we try to run, limit it to 3 processes for that user, and we try and run 4 processes, for example, 4 versions of top, then the container won't be able to start because it hasn't got enough memory. And so there's this weird trade-off between how many processes do you want to allow and how many processes would actually kill your system. Thankfully, in Docker 1.10, this has been fixed. And so Docker now respects how many forks a process can make. And it's already in RunC, which is like the base foundation for running container technology in Docker's open container initiative. And so hopefully in 1.10, it will be fixed, and things like fork bombs and infinite process forks will be resolved, which will be good for us, because it's a pain to get around. Beyond this, we have issues with logging and disk space. So someone thought it would be really clever just to do a while loop, which just spat out things to the log console. But the problem is, anything which gets wrote out to the console gets logged with Docker. And so very quickly, because it was on a very quick host, which wasn't doing much, the log file grew rapidly. And they couldn't stop it because it kind of took over the entire system. And so the disk, because I had forgot to move it, filled up and everything broke. Not great. Thankfully, in 1.8, this has now been resolved. So we've got log rotation. So again, Docker's realized some of the weaknesses and some of the aspects and some of the problems. And so as long as you set the right parameters, you automatically protect yourself against these problems. But that's not the only issue what you can have with disk. It can just fill up naturally. So for example, fallocate, we tried this and it said operation not supported, which we thought was fantastic. No one can just rapidly, quickly create a file. The problem is that's actually dependent on your the format of your disk. So ext3 did not support it, which is what I was running on originally. But when we upgraded to ext4, suddenly everyone could use fallocate to allocate gigabytes of empty space. Not great. But with Linux, there's multiple ways to solve different problems. So they could have done truncate or they could have done DDD. Again, it's not great. And managing disk and managing disk space with Docker is actually particularly difficult. They said use device mapper, but I'm sure some of us are aware device mapper doesn't actually work as described, and there's lots of performance issues. And this is one of the issues which we still battle with. There's also issues if you can look after the diff directory, that's one way to aspect it, but even they can just write it into other directories. For example, there's a host file which maps to a different directory. So we limited the first one. For the example, we limited the diff, but then they just found a way around it and wrote to a different file which they had access to and it still filled up. So still not ideal. And then finally, bandwidth. Bandwidth, again, is a problem to restrict. And basically, there's not much. Docker says how much bandwidth the container is using. You can set some weights, and so you can use traffic shaping to slow down certain traffic. But if they still want to get access, they will still use bandwidth. So again, not something ideal. And these are kind of the 3 issues which we really faced when we were getting started, and some of the core issues which we had to resolve. CPU is great because CPU shares did actually resolve a lot of the issues. The fixes for fork bombs and stuff like that coming will be better, but disk space and bandwidth, not great. So we looked at ways to resolve this and how could we secure what we had built. So the first thing Docker does out of the box is Docker diff. So this allows you to see the changes what happened on the file system and within the container. So if the user's creating huge big files, you can see what changed and you can detect it. And there's also things like bash history, so you can detect what changes and what commands they had run. But as we learned from Mr. Robot, not making history and not adding things to your bash history file is not that difficult. You just add an extra space and it's not logged. So we needed other ways around it. And so we created something called the Warden. It's basically a process which sits on every single box in our cluster, and it just monitors for potentially things which we think is malicious. It uses the API, which actually tells you a lot of the information which I described was problematic to restrict. So it tells you how much disk space the container is using, how much bandwidth the container has got in and out. And so we can use that and help protect our system. And then if we see anything malicious, we just close it down and stop it, everything's fine. But what happens when it does actually all go wrong, and what happens when all of the limits we put in place don't work? And so sometimes it's very simple. Sometimes you get told to run this nice little cute kittens container, and it says, well, you can't run it, you have to give me the Docker socket file, because that's what I need in order to run it. And so you give it that, and it runs, and it shows you beautiful kittens. Great. But the problem is, under the covers, because it's got access to the Docker sock, it can do whatever it wants. So it can launch privileged containers. These privileged containers could mount the volumes, and then they could just completely wipe your disk. And so having access to this file is problematic and concerning. And so we shouldn't give it away just quite freely as what we do to things like Nginx proxy, which is thin on the front end. So if anyone hacked that, they would access to your entire daemon. So that's a problem. And also you'll get emails from your hosting provider when they become unhappy because your box has been hacked. And you'll log in and you'll see a beautiful graph which has got 560 megabits per second. And you'll instantly go, oh my God, how the hell did I manage to generate that much of data? Like my blog's happy and it's busy, but it's not that busy. This is insane. And then you'll realize everything's running in a container, so it's not that much of a problem. Right? They couldn't have actually got access to that much. And then you start investigating what they did. And so you can use the logs, and so you can see all the nice happy stuff which they tried. And because it was Elasticsearch, they could run Java file and run Java snippets. And they did like wget to download stuff and execute files, which kind of added new files. And you could see by using Docker diff what had changed. And so they changed like netstack, PS, SS, added some configuration for security. And then they added these like DDoS 99 and DDoS 8, which I imagine what generated all the traffic. And so because it was a container, I could see exactly what they had done. I could see how much impact they had had. And I could just delete it and be confident that they didn't actually have access to the whole system. If I'd actually configured the container properly, they wouldn't have been able to do this. Because if I'd run it in read-only mode, Elasticsearch would have been able to write to the data directory, but it wouldn't have been able to write to the temp directory. And it definitely wouldn't have been able to write to the bin files. And it would have limited and it would have errored. And the container and Docker itself would have kept the system very nice and very secure by default, even if people are stupid and don't offer security onto their Elasticsearch instance, like me. And so these are some of the issues which we faced. And generally, is Docker secure? Well, we give people complete access to a Docker daemon and Docker containers running on our host. And so far, it's been pretty good. Yes, we've had to monitor additional things like disk and bandwidth, but generally, users can't break out of a container that easily. And as such, at the moment, no one's come up with a proof of concept exploit for breaking out of a Docker container, apart from one of the very early versions which didn't really count. The Elasticsearch hack, if it wasn't running in a container, it would have taken over the entire box. I would have had to completely destroy it and rebuild it from scratch, because I couldn't have been confident about what impact the hackers had had. If I configured it properly using read-only, it would have been even less of an impact. They wouldn't have even been able to launch the DDoS in the first place. And I've kind of poked fun at the naughty bits, but Docker itself is focused on security. They're doing a lot. The future versions are demonstrating that. And so it's a good and it's a nice system for us especially, because we can be more confident that Docker taking care of that, and we can just focus on our product and our platform. And it's a new rule, so you have to play by new things. Yes, we need a Warden, but you know what? We already need monitoring systems in place anyway, and so it's just an extension to that infrastructure. And with that, I'd like to thank you for your time, And if you have any questions, then please feel free to reach out to me afterwards or in the pub later. Thank you.